This presentation describes the profitability enhancement work that I do under the banner of Supply Chain Math or Supply Chain Analytics for Performance Enhancement. Before I begin, I'd like to introduce myself. My name is Ajita Kini, and I have been working in the area of supply chain management since 1994. I was graduated from the Indian Institute of Management, Ahmedabad in 1989, after which I worked in the IT industry for about 5 years. I then moved into supply chain consulting, first with Coopers & Lybrand, which subsequently became PricewaterhouseCoopers, and then with KPMG Consulting. In 2000, I joined Infosys in the Management Consulting Division and was based out of the US, initially on a sales deputation, and then working with a major retailer, implementing their turnaround strategy focusing on the supply chain aspect. I returned to India and freelanced for about 3 years before working with a couple of family-managed businesses on various strategic initiatives. I then moved back into freelance consulting and am now focused on supply chain management with specific emphasis on mathematical analysis and modeling in the supply chain area. If you look at any manufacturing operation at a very, very simplistic level, it essentially buys some inputs, converts them into something else, and then sells the finished goods. As the complexity increases, either because of increased scale or because of geographic dispersion, we create functional specializations. And as each function grows and improves its own working, we move towards local optima at the cost of organizational performance. Some common examples we come across very often are to do with input material procurement. Often the input specs of input materials can vary within a range with a corresponding impact on purchase price. These changes in technical specs often have an impact on the production throughputs, efficiencies, recoveries, or yields, and therefore costs. It is not feasible for procurement people to fully understand the impact of every change of technical spec in the input material and evaluate which material gives the business the highest profitability after taking into account both purchase price and changes in yields and processing costs. This is where a mathematical model can capture the economics in its entirety and enhance profitability. Similarly, there are opportunities when multiple products can be made at multiple plants. In such a case, deciding how much of what to make at each plant itself presents an opportunity. I will give examples of each of these on subsequent slides as I describe actual projects that I have undertaken. The first example here is of a copper smelting unit, where besides copper, sulfur oxides in the ore yield sulfuric acid as a byproduct, which can be either sold or used to produce fertilizer. Since the relative profitability of each product can change on a day-to-day basis, the optimization model helps the unit head decide what mix of products to produce to maximize profits. Taking the copper unit example further, in a multi-plant situation, we could build in the demands at different geographies and enhance the model to define how much of what to make where, as well as what distribution mode we should use to maximize profit. Going to another project that I did at an aluminium rolled products business. Here, multiple products could be made at any of 5 plants. The plants were all different, so the throughputs, yields, costs, etc. at each plant for each product varied. The operational challenge facing us was to decide what volume of each product to load on each plant to maximize profits, and therefore maximize ROI on investment in capacity. Given that demand was slightly in excess of capacity, the model also helped us define what orders to short fill or refuse. Once the model was in place, the same model can be used to evaluate capacity enhancement proposals by comparing the profits that are possible with or without the enhanced capacity and computing the likely payback period for each option. On another level, the model could also be used in annual sales target setting by evaluating the optimal product mix that would maximize profit given the capacities available. This is again something that I undertook at the copper unit, where different ores or concentrates have different chemical and metallurgical compositions. And these need to be mixed in various proportions to ensure various ratios remain within certain ranges for technical or economic or safety reasons. So we looked at optimizing the blend to maximize throughput through the smelter. This is what I was referring to on the opening slide when I spoke about the choice of input material determining the cost of material in the finished product. At a chemicals plant in Thailand, I used linear programming to develop a production plan. Here we had multiple products, all contending for common resources, such as the kiln or spray dryer. The challenge was to determine what volume of each product to take up so as to maximize demand fulfillment and minimize plant idle capacity. This is something I have not yet done in the field, but it would be entirely possible to develop a model to evaluate how much of FG we should hold at various stock points. The idea being to simulate changes in demand and use this simulation to determine optimal inventory holding patterns at various points in the distribution network. Going back to the copper unit, where we had a captive power plant, we had different kinds of coal that could be used with each of 4 different boilers to generate steam, which would then be delivered to one of 5 turbines to generate electricity. The optimization model sought to minimize the cost of electricity consumed by defining how much of which coal to use in each boiler, as well as for how many hours each boiler and turbine should run. The grid power aspect was also incorporated into the model so that any excess or shortfall could be sent to or drawn from the grid. That is why the objective was defined as minimizing the cost of power consumed rather than minimizing the cost of power generated. All the models I've talked about till now have been linear programming optimization models. This one, which I'm showing you now, was done at the chemicals plant at Thailand. It was a regression model used to predict the price of phosphoric acid. This is a key input material for them, and the price fluctuates greatly. By predicting an upward or downward trend, we could quickly decide whether to stock up or liquidate phosphoric acid stocks. To do this, we studied the methods by which phosphoric acid is produced and tracked the prices of those input materials to develop a price prediction model. If you look at the data, the price hovered around 700 USD at the time, and our predicted prices were coming within plus minus $10 of the actual. More importantly, the model forecasts the trends correctly. This is not a mathematical model, but an approach to help in defining inventory holding norms. It is more useful in defining inventory holding norms for spares and consumables rather than for RMPM. Typically, when inventory categorization is done for accounting and valuation purposes, an ABC or XYZ basis is used. Whereas from a plant operations point of view, the VEA or Vital Essential Auxiliary categorization is more relevant. So to decide spares and consumables inventory holding policies, we need to categorize inventory by multiple methods and use a combination to define the holding policy. For example, if there is a high-value engine that is required to be held, it would be a low-consumption but high-value and vital item. In a multi-plant situation, it would be best to hold a single piece in a single location and airlift it to wherever it is required whenever there is a need. Whereas a vital but C and Z category item can be held at each plant. Policies relating to usability certification would also need to be put in place. There is no point carrying a spare gasket and discovering it is not usable because it has been lying around forever. End-to-end supply chain alignment is a core offering. I have been working in this area for over 15 years now. Essentially, the focus of work here is to reduce the working capital cycles, enhance OTIF levels, reduce inventories, etc. by analyzing the supply chain in its entirety rather than viewing it through any functional lens. This is typical process-oriented work. This is something I did at a spinning and weaving unit in Haryana. Here, various improvement initiatives were identified and worked on by the in-house team itself. The enhanced targets were then incorporated into the 2013-14 budgets by the implementing team, which speaks of a certain confidence that the benefits will be realized. To summarize, there are various kinds of projects that can be taken up. Some of the models relate to operational decision support. Examples are product mix decisions, production planning in single plant or multi-plant situations, transportation logistics planning, which is both the mode and the route, procurement timing, feedstock blend composition and procurement, captive power generation modalities, stores and spares inventory holding policies, or cash-to-cash cycle reduction process design. There are also models that can be used for strategic decision support, which include capacity planning given the product mix and demand estimate, product mix planning given a capacity and pricing or costing estimate, and distribution network planning. The tools I have been using in all these projects are essentially linear programming and operations research, regression modeling, correlation analysis, factor analysis, and process mapping and analysis. Thank you.